Very good afternoon, and thank you very much for joining this talk. Really happy to be here talking about throughput improvements with JSON workload. My name is Gireesh. I work for IBM. The objective of this talk is probably twofold. One is to discuss the basic philosophies and principles of node.js, that is the event-driven architecture with functional programming style that is single-threaded, and then discuss and examine how we leverage this philosophy and principles to the next level. How do we extend that to address some of the most common programming problems in the modern workload? So that's pretty much the agenda is. For people who are familiar with the Node.js principles, the first part is probably going to be pretty straightforward and probably a context setting for the second session. For whoever it is new to Node.js, it's going to be chapter number 1. So let's look at what is the problem which Node is trying to solve. Look at this chart. So this is basically showing the time that is taken for a piece of data, that's a byte of data, to be transported from one endpoint to another endpoint in a computer system. So endpoint would essentially mean a location in a distributed computing system where you can store a byte of data. As you can clearly see, the number of rows can be clearly classified into two. The first one being the CPU registers, the cache, and the memory, which probably takes comparable amount of time between 0 and 100 nanoseconds, whereas the next set of things, that is the disk, the secondary memory, and the network. In this case, in the network, we are passing a byte of data between California and Netherlands, and it comes back. So it's pretty huge, 10 millions and 150 million nanosecond, that is 150 millisecond. Now, what is the problem with this? If you look at a most common web app, the SLA, the service with the clients become extremely critical. And if you have number of backend services which the web app is trying to connect to, these, each of the backend connectivity requires network access, and the 150 millisecond which we are talking about is going to linearly increase, and you are going to break the SLA. Now, how the legacy, the traditional language runtimes and the virtual machines used to address this problem? They implement something called as a thread pool, where you pre-create n number of threads, and each thread wait for a client to be connected. As in when the client is getting connected, the thread gets dedicatedly working for that particular client. So what that means, at any point in time, if you take a thread dump of your web app, you see 95% of the time, all the threads either waiting for a disk I/O to be completed or the network I/O to be completed, either read or write. Now, what that means to the machine, it essentially means waste of time, waste of effort, waste of CPU resources, while you create a lot of threads and thereby hold up a lot of resources, the actual throughput is being compromised. So that's the problem which Node.js is trying to solve by multiplexing or reusing the time that's spent on the network I/O or the disk I/O by switching between tasks with a single thread. Let's examine how it's implemented. So look at this particular slide. In the left-hand side, you have a number of functions which are accessing the disk or the network. The first one being a DNS lookup, which definitely is a network computation. You need to perform a DNS lookup. You extract the activity that's required, put it into a data structure, and pass it on to an abstraction called libuv, or an event infrastructure, which knows how to perform this network lookup in an asynchronous manner, and you delegate those activities to the operating system, and you continue the execution. So the 150 millisecond which we are talking about, that's going to take for the DNS lookup is actually delegated to the operating system, and you continue to perform the next action in your program, which happens to be a read file, which basically having a disk I/O. So the activity continues, you compose a data structure and request the kernel to perform the I/O operation, and you continue. So you don't really block on any activities that requires huge amount of I/O activity. The third one is a typical TCP activity, and it follows the same suit. The fourth one is something called as a scheduled function. It's a mimicking of an I/O activity. You don't have an I/O in the background, but you just schedule a function to be called after some time. The last one is a pure CPU-bound operation. You just want to print something onto the console. Now, if you look at the right-hand side, you see the last activity that was appearing in the program is basically being output first. So that's because you don't block anywhere, you're able to execute right in front. And the next one happens to be the file system callback, and the next one, the DNSCB. So the essence of this slide is that you are able to execute things in the way which your system is able to complete those actions. You don't really block anywhere. So with this approach, a single thread is able to manage all sort of workload, which is basically a mixture of I/O and the CPU bound. Now the dark purple circle in the middle, which is carrying out the magic of transporting your I/O bound operation to the kernel and calling back on your program when the actual I/O activity is completed, is called the event loop or libuv. So that's essentially the fundamental premise of event-driven architecture. Now, one of the most common questions which the traditional programmers ask is, for example, you initiated a DNS lookup, you initiated a file read, you initiated a network access, but remember, you did not complete any of them. All of them are pushed onto the operating system queue, and after some point in time, when you actually come back, when the kernel responds with the data, how are you able to bring back the context? That is, I want to perform some next level of activities on the result that's coming out of the DNS lookup. So how do you get back the context? That's the next question which requires to be answered. So the answer lies in functional programming. Functional programming, pretty straightforward, a paradigm in which computations are evaluation of functions. Basic unit of computation is functions. It's a direct definition. Most of the programming language have functions, and all the computations go inside a function. Functions as first-class variables. This essentially means the functions are treated as pure variables. That means you can assign a function to a variable, you can pass a function to another function, you can return function as a return value. The last line shows a classical use case of higher order functions, which is a function as first-class variables. It's a real NLP pipeline. You would see that sentiment is basically a result of a function called compute score, but actually the first three parameters to the function, that is meaningful words, two lowercase, and the words, all of them are really functions. The actual data is the last parameter, which is input. So input data is applied on the words function to extract the words out of the data, and then it is applied onto two lowercase to get only the lowercase data elements. Then out of that, you extract the meaningful words and finally compute the score. So this is basically similar to the higher order functions that is common in mathematics. The essence of this slide is to say that the sentiment, that's the output, is basically a higher order function, higher order dependency to the input, and where these different levels of order is affiliated to different set of functions which are just used as any other variable. Closure. Closure is a powerful construct in functional programming paradigm. It's basically the operating environment of a function. The closure remembers the code that is defined in a function and the operating environment in which it is defined. So what that essentially means, if you look at the left-hand side program snippet, you have an outer function which is set up, and it defines a local variable called buff, and then it defines an inner function called pileup. Now remember, the inner function is defined in the lexical scope of the outer function, but the key characteristic of the closure function is that it lives outside the scope of the outer function. So once the outer function completes its execution, still the pileup function lives through, and not only that the inner function lives through, the local variable that was defined in the lexical scope of the outer function also brings to the life because it is required by the inner function. So the essence of this slide is that the inner function retains the context in which it was created, as well as all the variables, all the operating elements that the inner function was requiring to access has been kept as a snapshot for future use of the inner function. That's exactly the closure. Why the closure came into the discussion here? So probably that's the answer to the question which we asked in the slide. When the I/O bound activities are pushed onto the kernel and executed in a future point in time, as and when the resources are ready, and when you come back with the data, what is the context in which you are going to execute those callback? What is the context in which you are going to execute the post I/O activities? Closure is the answer. So that actually answers another question, that is why JavaScript was picked up by the Node.js. I don't have a documented answer to that, but probably my answer is that closure, that is the powerful feature to implement the context-aware function, is the single reason why JavaScript was picked up for the event-driven programming model. Yesterday somebody talked about JavaScript being dead in the 1990s, and then it's surprising to see that it's the most popular language. So I would attribute the resurrection of this language to this particular feature called closure. So it's in most of the other programming languages, it's called as Lambda, and at the time when Node.js JavaScript combination was implemented, Lambda was not there in most of the modern high-level programming languages such as C++ or Java. Right now, I guess both the languages have it. So that essentially is the first part. Now let's look at the problem which we are trying to solve, JSON in the modern workload. So JSON doesn't need any introduction. It's basically invented to exchange very tiny data between client and server. JSON stands for JavaScript Object Notation. Over the time, it has become the de facto standard for any sort of data transport between endpoints. And it is understood by the JavaScript language natively. The format in which you write the object is the actual format in which the JavaScript objects are either represented or modeled or stored in the memory. So that means to say, if you want to marshal a JSON object, it becomes a native operation. It becomes just an assignment operation in the JavaScript world. If you want to unmarshal, that is deserialize a JSON object, you just need to, I won't say cast, but it's a primitive operation in JavaScript. Whereas if you look at any other language, you need to implement adapters or custom libraries to process the JSON data. Now, what is the issue with JSON in the modern workload? As we know, it started with a tiny data exchange, but over the time, especially in the cloud deployments, you see most of the endpoints, microservices or backend services, basically talk between each other through JSON workload. And if you look at unstructured databases, most of the unstructured data is stored and retrieved with the JSON wrapper around them. So over the time, when the volume increases, what happens in the Node.js deployment? As we saw in this particular slide, all the IO-bound operations are pushed onto the kernel with the event machinery, whereas all the CPU-bound operations are carried out in line. And remember, you only have one thread, and this model perfectly worked because with one thread and with all the IO-bound operations pushed outside of your thread, you are able to execute 10 to the power of 6 instructions while 1 byte is moved from one location to the another in the disk or the IO channels. But when it comes to JSON processing, you have huge amount of computation that is required, and the 10 to the power of 6 instructions probably is not going to be sufficient if the JSON payload is huge. So what that means? That essentially means your responsiveness is getting affected badly. Now, is JSON the only CPU-bound operations in the Node.js workload scenario? Not necessarily. You have HTTP parsing, you have a couple of other items which are known to eat up CPUs and thereby throttle the single thread in your transaction. But Node.js has cleverly sidelined those CPU-bound activities within the API framework itself with the help of internal worker threads to carry out those CPU-bound operations and come back to the main application thread as and when the parsing or other CPU-bound activities are completed. So that way, we don't really see any problem with any of the HTTP workload coming and eating up CPUs. But JSON happens to be an exception. The natural question comes is, why can't we offload the JSON work to a helper thread? That's not possible because Node.js leverages the V8 virtual machine, V8 JavaScript engine, which is having a single threaded architecture with one JavaScript heap that assumes single thread entry into the heap and object access. So JSON works with the JavaScript objects, and JavaScript object cannot be accessed by another thread. So that means to say offloading the JSON work to an internal worker thread is architecturally impossible. So that's the problem which we have been trying to solve. So let me show a demo. So what we did is we implemented something called a yieldable JSON. The whole idea is look at the premises of Node.js, that is push the work to its boundary and come back to execute the rest of the thing, and then go back and visit those workload later when you have some leeway. That's the philosophy which we want to implement. So in the yieldable JSON, what we saw is once you enter the JSON processing, it takes probably a few seconds before it comes back to the UV loop or comes back to the concurrent clients which are waiting to be processed by the server. So what we did is we looked at ways how can we chop the work into multiple pieces. One of the challenge is once you enter a graph or a recursive loop, there is absolutely no way to come out of it without really losing the context. Now, if you are re-entering the loop, you are again executing right from beginning. So we need actually a construct or a programming semantic that help us to retain the context of our traversal and come back to a position where we can address the waiting clients and go back to the JSON processing, resume the activity at that point in time. So that resembles the closure context, but closure is not going to help over there because it helps in retaining the contextual data. It doesn't help in retaining the contextual control flow. So then we researched and looked at various semantics and stumbled upon something called the generator semantics, which is available in ES6. So the yieldable JSON is an asynchronous JSON module which leverages the generator pattern and basically incrementally perform a CPU bound operation, customize how much you want to traverse, and stop at some custom point. When do you think that your clients are waiting? You need to go back to the main thread. Sorry, you need to go back to the event loop, get the sockets and perform activities, and go back, get the context, and continue the execution. So let's look at that. So I have this 25 lines of code. I create an HTTP server. I source in the yieldable JSON module. I read from a huge file which has a JSON data, and then I parse it. Then I set up the server. Server takes two parameters. One is an async mode and a sync mode. If it is in sync mode, I stringify the parsed object and pass the stringified object to the client. In the async mode, I call the stringify async function or the yieldable JSON and then wait for the data to be completed. Once the data is ready in an asynchronous manner, I respond with that to the client. So that's the whole logic. So first I run in the sync mode. It takes some time for the JSON data to be loaded from the disk in a synchronous manner and then listen at a port. So it's ready with the data. So in this terminal, I start 100 clients. So as I said, the JSON data is around 80 MB. So the time interval you see in between is the time taken by the server to stringify the JSON data and pass on to the client. So clearly, it takes around 2 to 3 seconds, which is in an enterprise deployment is unacceptable for the SLA for a web app. So I stop the server. I run it in async mode. So as I said, in async mode, you execute this piece of logic. You basically get the data and pass it on to the yieldable JSON. So wait for the JSON to be parsed and the server to be up and running. And then I start the same set of 100 concurrent clients. So I see all the clients are able to be processed at the same time, or the delay is negligible, right? So I get the same concurrency level as any other IO bound workload or any other workload which do not have high CPU intensive operations. So that's pretty much the logic is. Now, this is the NPM module which we are talking about. This is the key function, stringify async and parse async. Stringify async takes 5 parameters. First one is the object itself, which you need to be stringified. Next one is a replacer. While stringifying an object, if you want to replace some of the key or values with custom values. Next one is a space, how much is the indentation you want to apply. And the fourth parameter is the key one, fourth and fifth. Fourth one is an intensity, fifth one is a callback. Unlike in the JSON.parse and JSON.stringify, which is a synchronous activity, it just returns you the value. Here it's an asynchronous one, you get the value in the callback. Now, what is an intensity? I just shown you the default intensity. That means to say, when you enter the JSON workload, at what point in time you want to come back, right? That basically depends on what is your SLA with the clients. You could choose to complete the JSON operations and come back. You could choose to, run through one or two key objects and come back. So there is always a trade-off. If you come back immediately, your JSON parsing is going to be delayed. If you come back at a very later point in time, your waiting clients are getting affected. So look at your workload situation, benchmark it, calibrate it, and see what is the right amount of traversal that your JSON activity needs to perform, and then set that as the intensity. So by default, the intensity is 512. What that means is, once you enter the JSON processing activity, you process 512 objects before you come back and check in the event loop. So because the workloads are heterogeneous, each application is unique, we thought we should parameterize the intensity so you can test and try run and basically zero down onto a particular value which best work for your situation. So iterator pattern, just a context about what is that pattern about, is an enumerator interface which traverses through the container of a components in a container. Generator pattern is the one which we just talked about. It's a pattern in which you can incrementally traverse in a data structure and control the customize the control flow within that particular data structure. So these are the JSON in the Node.js existing art. The first two are synchronous JSON. First one is the built-in API from the Node.js API library. Second one is a same implementation but written in JavaScript. First one, by the way, is a C++ implementation. Third, fourth, and fifth are kind of asynchronous parser implementations but not completely functional. They either leverage the existing V8 implementation or do not have the counterpart APIs. The last one is the one which we just looked at, and here is the data. So the data elements which we are looking at is based on the loop availability, not really on the performance. We are looking at the throughput, we are looking at how do we address the concurrent clients to be served better when you have huge amount of JSON workload in your application. So the first two basically are same implementation in two different languages, JSON and JSON2. You have for 60 MB of JSON data, you have this amount of latency. That's the number of milliseconds before the single thread node is available in the loop to access the next set of clients. The last one, because we custom tailored the loop availability, we could choose what is the interval in which we want to revisit the event loop. It's always constant, 5 milliseconds, without any standard deviation. So that perfectly work for your workload situation. That's pretty much I want to cover. So these links basically have all the material which I talked about: functional programming, continuation parsing, style, closure, context, etc., and the package link for yieldable JSON and the GitHub URL. So yieldable JSON is just an example. We do several such research year on year. Basically, the bottom line of my talk is basically to say that Node.js provides the principles and philosophy of an event-driven architecture with functional programming style. It is up to us to see how can we leverage and extend those principles to address the problems that is, present in the common workload situations. And by continuously looking at that, by comparing the principles, we should be able to come up with solutions. I can think about a number of other problem scenarios in the modern workload. For example, how do we improve the performance of microservices with the Kubernetes and the other clustered orchestrations? Performance have come down a lot. How do you improve that? How do you basically address the stream back pressure? And a lot of such problems exist in the modern workload. How can we leverage these principles effectively to see how those things can be resolved? So that's the essence of my talk. Thank you very much for listening.